It's good to be back here at Q2B. So today, as you mentioned, I'm going to be telling you about what we might actually do with error-corrected quantum processors. So as you may have heard about earlier today, at Google, we are very focused on building an error-corrected quantum computer. We have a 10-year timeline to do that, and we're intending to build a device with about 1 million physical qubits. However, in the meantime, we're going to continue to still have NISQ devices, and we're working on making those devices accessible via cloud. And in fact, we already have external users using those devices in that capacity. And we're still going to continue asking the question, what can we do with the devices we have? And so, in fact, if you want to hear more about that, there's going to be a talk later in the week from Nick Rubin that's about the largest quantum chemistry simulation performed on a NISQ device, which we recently published in Science. But today, I'm really going to focus on error correction. And I think that error correction is sort of inevitably the future of quantum computing, but it's also very expensive. So the first thing you should know about error correction is that it's very rigorous. It's based on proofs, and it's based on the resilience of topology. So, sort of unlike in NISQ, things that work on paper, we expect them to work in practice always within error correction. So, for example, once we have high enough fidelity 2-qubit gate operations, and fidelities we've already reached, 99% about the threshold we're looking for, error correction allows us to exponentially suppress errors just by increasing the number of qubits. So with 99.9% fidelity gates, most algorithms would require about 1,000 physical qubits to encode a perfect logical qubit. However, there are other costs as well. It turns out that certain gates that are necessary to be universal, in particular T gates and Toffoli gates, have a very large overhead within error correction. To give some sense of this, I want to emphasize that to implement, say, a NAND gate in CMOS, with classical transistors, this takes a few transistors and it's much quicker than a nanosecond. So we might say the space-time volume required for that is about 10 to the minus 9 transistor seconds. By contrast, and I won't get into detail about what this diagram is, it's showing the stabilizer measurements for error correction. But to implement the equivalent of an AND gate within quantum error correction, which is sort of the distillation of a Toffoli state, this requires more than 10 qubit seconds. And that's a big overhead. We have, just very heuristically here, about a 10 orders of magnitude slowdown. And that is going to have real consequences for us, which I'm going to discuss now. In particular, I think we really need to take a critical look at the idea that we might be able to realize quantum advantage with quadratic speedups within error correction. So many quantum algorithms are very popular, Grover search or algorithms for Monte Carlo, they give a quadratic speedup. Also, quadratic speedup, I would say it's the usual hope for most heuristic quantum optimization algorithms. Optimization is NP hard, so we can't get an exponential speedup in the worst case. So I think, a lot of the arguments for, say, the adiabatic algorithm or variance, things like that, are hoping for a quadratic speedup. So if we have a quadratic speedup, we might say there's a classical algorithm that takes time c times n, where c is the sort of constant factor of the classical algorithm. We have a quantum algorithm that scales as q times the square root of n, where q is the constant factor of the quantum algorithm. And basically, if we're in a situation like I'm describing where q is much, much larger than c, then we need a very large n for this quadratic speedup to actually overcome that constant factor and win out. By contrast, if we have an exponential scaling advantage, then this gap's going to close very quickly, and we shouldn't be so concerned about this. So making matters even worse is the fact that many applications where you can get a quadratic speedup on a quantum computer, like Monte Carlo or search, they turn out to be embarrassingly parallel classically, and that has real consequences as well. So I'm now going to, and in particular, quantum error correction requires a whole cluster, so we should probably not be comparing to just single classical CPUs. So I'm now going to get, again, a little bit more detail about what numbers might look like for quadratic speedups here. We had a recent paper out, which I'm citing here, where we compile a bunch of heuristic algorithms for optimization to error correcting codes, and we look at the overheads. We looked at things like QAOA, Grover's algorithm, and a quantum algorithm for simulated annealing that gives a quadratic speedup over classical simulated annealing, among other things. And so we asked the question, how long must, for example, the simulated annealing algorithm run until the quadratic speedup overcomes the constant factors. And we looked at very fast implementations of simulated annealing on a classical computer and compared that to our best compilations of this quantum algorithm for simulated annealing. And when you're only comparing to a single classical core, the crossover time was already quite discouraging. It was around 320 days. And if you are able to parallelize the classical side over, say, 1 million cores, it's even much more discouraging. So we also put out a paper very recently which argues for sort of a lower bound on, if things went as well as possible for the quantum computer for some sort of generic algorithm with a quantum speedup, what might be a lower bound on the crossover time? And you can see the details of this analysis in the paper, archive paper I'm quoting here. But already, if we're comparing to just one classical core, maybe it doesn't look so bad, 2.4 hours, but this is a very, very loose bound. But if you could parallelize over even 1,000 processors efficiently, then you'd require over 100 days, which is looking extremely discouraging. We repeated the analysis for other types of speedups, cubic speedups and quartic speedups, and we find that quartic speedups are already looking a lot more practical. So on one hand, that's encouraging, but it turns out that even if we were to speed up the rate of the error correcting gates by a factor of 100, it doesn't fundamentally change the conclusion for quadratic speedups. So I think that's really a big indictment of quadratic speedups within error correction. So what other algorithms might we be interested in realizing with an error correction? Well, linear algebra, it's a big application of quantum computers. There's this so-called Haro, Hasidim, and Lloyd algorithm that solves linear systems of equations, AX equals B for X, for an M by N matrix A. And in principle, you can get an exponential speedup over the best classical algorithms here because this takes time that's only polylog n, whereas it must take time polynomial n on a classical computer. But there's a lot of caveats here in order to actually realize quantum advantage. For example, the condition number of A is going to need to scale polynomially in n. A has to have some special structure that allows for efficient simulation. B has to have some efficient structure or special structure that allows for efficient state preparation. And ultimately, you're going to have to sample the quantity of interest from the state, the output state that you prepare, X. And in some cases, that could negate the speed up as well. So in what context might this be useful? One area that there's been a lot of focus is using it to solve differential equations. You can use a linear system solver to implicitly solve some partial differential equations. In particular, this looks practical when the differential equations are linear or at least have some bounded nonlinearities. Furthermore, though, it's going to be critical to find differential equations that cannot be solved by Monte Carlo because classical Monte Carlo also has a scaling which is independent of the dimension. And in such cases, you could probably only get a quadratic speedup on a quantum computer, but as we described, that's not what we're looking for. So we probably want to find a problem that has a so-called sign problem in it. So I should say there's no really fully fleshed out verified use cases for solving differential equations yet, but it's definitely something that's worth exploring. We're working on it at Google. I know a number of others are as well. So it's definitely a good application to keep in mind. How about quantum machine learning? This is, of course, an area that there's a lot of work in, and you hear a lot of talk about it at this conference. There's certainly many rigorous examples of getting a quadratic speedup in quantum machine learning, but as we've discussed, that's probably not what we're looking for. There's also a number of quantum machine learning algorithms that are based on the HHL algorithm, the linear system solver, but they require QRAM. And if you actually look into the cost of implementing that QRAM, it tends to negate the overall speed up. So that's also not what we're looking for. But there is this broad area of quantum machine learning, which is mostly what people focus on in NISC, which is just sort of based on the observation that quantum circuits can, and we know that they can, sample from classically intractable probability distributions, and machine learning is really about representing probability distributions of some data. So the real question, though, is, are these probability distributions that you can sample from on a quantum computer, are those really, do they really need these, or do classical data sets you might want to model really need, these quantum correlations? And to that, I think the answer is perhaps, or maybe even probably, but how common and how important are those tasks? How likely are you to actually encounter data sets that require entangled quantum state for its description? So that's kind of an open question, and it's something that we need to keep looking into. I think this is also sort of a central question for NISC. Really the essential question of why is quantum machine learning going to be useful at all? And it's something that's not answered, so people need to keep researching it. Our team's been working on this. There's some recent work I don't really have time to go into, but it starts to, I think, elucidate, for what types of classical models of machine learning you might be able to get a speed up over with a quantum computer. Okay, I've gone through applications in linear algebra and machine learning, but the original application of quantum computers was for quantum simulation. So is that going to sort of save the day for error-corrected devices? It might. There are many exponential speedups that are available in simulating physical systems on quantum computers. But I think a question that remains is there going to be a large enough market in modeling physical systems to justify the large investment that will be required to build a fully fault tolerant quantum computer? And I think for that, in our minds, we're hoping for a market that's on the order of at least tens of billions of dollars a year. And I'm very optimistic about this, but we'll have to see the extent to which that's really the case. So it's good to keep in mind in quantum simulation, there's really a spectrum of possible applications where on the left side, we have sort of the easiest things you could imagine, simulations of scrambling and black holes. They're very esoteric physics feeling experiments that are already similar to the random quantum circuits that we know we can go beyond classically tractable with today, even in NISC. Maybe moving a little further down the spectrum, you have lattice models you could simulate the dynamics of. They're models of phase transitions in condensed matter physics. They sort of look like our devices already. Going a little bit further, you could imagine using such simulations to simulate, systems of spins that really have a correspondence to something you measure in the lab, like an NMR spectra. And eventually, on the far side of the spectrum, you have something like a realistic description of, an important molecule that you might want to simulate. And I should emphasize that within NISC computation, it's really uncertain how far we're going to get along this spectrum. We've basically already or almost have gotten to applications on the left side, and it's kind of speculative the extent to which we're going to be able to get to applications all the way on the right side within NISC. We'll probably get somewhere in between. But for quantum error correction, it turns out that the gap between the left side and the right side of the spectrum isn't that huge, just due to the way the cost models work out. And so for that reason, a lot of the industry interest has been on these realistic models of that we might simulate, for instance, quantum chemistry, and in particular, electronic structure. So I'll say a little bit more about that now. Typically when we're doing quantum chemistry on a quantum computer, the goal is to prepare and analyze low energy states of chemical systems. So such calculations give us insights into the mechanisms of chemical reactions and also tell us, the properties of these low energy states, which predict the properties of materials and that sort of thing. An example which a lot of people might be bored of at this point, but is sort of a benchmark for the field, it's what we have numbers on, so I'm going to go through it, is this example of nitrogen fixation. So this is the procedure by which we make fertilizer. It's very important for all the food grown on Earth. And the way that humans make fertilizer, it requires very high temperatures, 500 degrees Celsius, very high pressures, 20 megapascal. It consumes about 2% of the world's energy. But there's a bacteria that lives in the soil that has this enzyme nitrogenase. And within nitrogenase, there's this cofactor, the sort of magic active site called FMOCO, which at ambient pressure and ambient temperature breaks this nitrogen triple bond to form ammonia, and does that with essentially no additional energy. So we know all the molecules involved, but how does this actually work? The mechanism is unknown. It's something we could resolve with quantum simulations. If we could understand that, perhaps we could make an industrially viable alternative. So we recently had a paper out, which I've given the reference for it here, which gives the lowest scaling quantum algorithm and the compilation with the lowest constant factors for solving such a problem. In fact, for solving this particular problem. At 10 to the minus 3 error rates, or 99.9% fidelity, we need about 4 million qubits in about 4 days of runtime. But if we can improve the error rate by a factor of 10, this drops to 1 million physical qubits in about 2 days of runtime. which isn't so bad. I mean, this is a problem that's quite intractable classically. So, it's an example of something we could use even a modest fault-tolerant quantum computer for. There's also sort of a different class of quantum chemistry calculations I want to talk about that pertain a bit more to simulating solid state materials. So, different representations of the quantum chemistry problem, they might involve different basis sets, essentially, which can lead to cheaper calculations. So when we're simulating molecules, we often use these highly detailed molecular orbitals. When we're simulating solids, we often use these more coarse plane waves. The molecular orbitals, they're very precise, but they're expensive. Already with 100 qubits, we could represent things like FOMOCO, industrially relevant molecules. With the plane waves, these are sort of cheap to use, but they're less precise. At 100 qubits, you could represent scientifically interesting problems, maybe not yet industrially relevant. In this representation, you might need a few thousand for that. But still, this is good for getting a sort of coarse-grained description of materials. And the plane waves are very good for modeling periodic systems because they are periodic. So like a crystal is periodic in 3D, or graphene is periodic in 2D. So they'd be pretty good for modeling things like that. And we've had a couple papers over the last couple of years that have optimized error-corrected quantum algorithms for simulating chemistry in this representation. And the costs here are much cheaper. So you need only about 300,000 physical qubits and about an hour of runtime to solve classically intractable instances at 99.9% fidelity. And if you lowered the error rate by a factor of 10, you'd be able to get away with just 60,000 physical qubits and about 30 minutes of runtime. I should also note that if one is, interested in a particularly accurate solid state calculation, there are methods that we have developed for that I've given the reference for here. We haven't fully compiled those to within error correction, though, and that's something that we're working on now. So the final thing I want to say about chemistry is just, a point of optimism. These algorithms have improved really rapidly over the last few years or so. I mean, I can remember quite clearly just 6 or 7 years ago, we were looking at algorithms that required runtime n to the 9, and we thought we'd need 10 to the 20 gates. And we're now looking at algorithms scaling as n to the 3rd and requiring about 10 to the 9 gates. The two tables here, I've shown the two different types of quantum chemistry calculations. On the top, it's the molecular orbitals, and on the bottom, it's the plane waves. So I have to think that we are getting within a few orders of magnitude of optimal compilations at this point, but there's still going to be ways to improve how we do quantum chemistry on quantum computers, and we're going to keep working on that, and these costs will keep coming down. So that's something to be optimistic about. So with that, I want to sort of summarize and wrap up the discussion here, just give sort of an outlook on error-corrected applications in general. I should probably start with something I didn't talk about at all, but which you might be wondering about, and that's quantum algorithms to break encryption, which is something we know quantum computers can do very well. And our team has some work showing that you could do this in about 8 hours with about 20 million physical qubits, and that's great. But what's the business application of breaking encryption? I'm sure there is one. I'm not sure it's something Google wants to be involved with. So we're not really focusing on that. We'd rather focus on more productive applications. Unfortunately, it appears that we do need to do better than broadly applicable quadratic speedup quantum algorithms. So, for example, I'm explicitly doubting the viability of algorithms for, say, options pricing in finance applications that are based on Monte Carlo if you're only going to get a quadratic speedup. At least on the first, few generations of fault-tolerant quantum computers, that doesn't seem viable. Machine learning and optimization are other areas that have very broad appeal, and we're going to keep working on them. But the most hope for a large speedup there is to focus on instances with a very specific structure, and that might deteriorate the broad appeal if they're only going to apply in specific circumstances. So we're going to have to see the extent to which that's the case. But the idea that there's really broad applications in those areas right now is still speculative. It might pan out to be true. We need to see. Quantum algorithms for linear algebra are really well developed. They can be formally studied. If we can find a clear application, then we can do a full compilation and really analyze the resources required. We need to find a problem that has a perfect fit, though, and that can be a bit challenging, but we're going to continue to do it. And finally, there are industrially relevant applications of quantum chemistry. which we've talked about, and one needs only a few 100,000 to a few million physical qubits for interesting applications there. So that's all I had to say today. Thank you all for listening, and I just wanted to quickly thank my frequent collaborators in this work.